Alright, today we're going to be doing a Born-Haber cycle. In this case it's for potassium fluoride. And so here is the reaction that we're going to describe today. We want 1 mole of potassium as a solid and half a mole of fluorine as a gas to form 1 mole of potassium fluoride as a solid. And so eventually our reaction is going to address that. But first we need to get everything so that we can do that. And so the first thing we're going to need to do is change the potassium from solid to gas, and we call that sublimation. And the next thing we need to do is change that potassium as a gas into potassium as a gaseous ion, and that's the ionization energy. In the next step of this problem, we need to take the fluorine that's covalently bonded together and break it apart into fluorine atoms. And so each of the fluorine molecules that are connected needs to be broken apart into its 2 atoms. Fluorine is a diatomic molecule. And so in that chemical reaction we had 1/2 of a mole of fluorine molecules, F2. Means if we break that apart we will create 1 mole of fluorine atoms. So 1/2 of F2 becomes 1 whole F. And so we need the energy to break that bond, and that's the bond dissociation energy. And the bond dissociation energy can be found on the problem here. The bond dissociation energy for F2 is 158 kilojoules per mole. And that's this number here that we need to add in. But we didn't break up a whole mole of F2. We only broke up 1/2 a mole of F2. And so what we need is 1/2 that number. And so 1/2 that number is 2 into 15 goes 7 times. 2 into 18 goes 9 times. And so that 1/2 number is 79 kilojoules. Right? Everything else so far we've done, we had 1 mole of potassium that we sublimed and 1 mole of potassium that we ionized. And so each of those steps is exactly that number, 89.2 kilojoules here. And then here for the ionization energy it's 418.8 kilojoules. And so we've added about 500 total here. We've added another 79 here by tearing apart the fluorine molecules. And so let me draw the picture of what we have here now. What we have now is our potassium gaseous and our fluorine atoms. And we have 1 mole of each of these already as gases. And we've come up in the 3 steps that we talked about already. So this was the bond dissociation energy, that last step, the ionization energy, the second step, and then the sublimation was the first step. Now we need to ionize the fluorine. And to ionize the fluorine, we need to look at electron affinity. And electron affinity, remember, is the release of energy. When an element in its gaseous state adds an electron, it becomes an anion, and then it releases energy. And so that energy is out, and so it has a negative sign. And so that means that's going to be energy back into the system. And so that's going to be the electron affinity. And then at that point we have our ion of potassium and our ion of fluorine, and we need to form that KF solid. And what's that big step going to be? That's going to be the lattice energy. And so for the last step of this problem, we need to actually put in all the numbers for each of these steps going up and going down to get the overall reaction. We started here with potassium metal and fluorine gas to create that Kf solid. That's the reaction we want the energy for, and so that's going to be the sum of all these. So it's going to be the sum of the 3 steps up and the 2 steps down. Now in this case we're going to find that the lattice energy is significant, and it brings that value to a negative overall value. This overall value is what we want. Where do we start and where do we end up? In some cases, because either the ionization energy is smaller, the bond dissociation energy is smaller, the lattice energy is bigger, or the electron affinity is bigger, you can actually end up with a slight positive value for the overall enthalpy of formation, or the enthalpy of reaction. So let's look at that right here again. So again, this is the reaction we want here. We want the reaction of potassium with half a mole of fluorine to form potassium fluoride as a solid. And so we're trying to find the net energy change when we do that. And so it's really the sum of all the parts. And so in this case it's the 89.2 plus the 418.8 plus half of the chlorine bond dissociation energy, and then we're going to be subtracting a whole mole of the electron affinity, and we're going to be subtracting a whole mole of the lattice energy. Is right, those electrostatic interaction is really just another word for the attraction of a positive thing and a negative thing. And so the ups, so in the last step of this problem we need to add up all the energy it took to get to the top. Okay, 1, 9 plus 8 is 17, 26, 27, carry the 2's 9, 10, 18, 1. So it took us 587 kilojoules to go from our potassium metal to potassium gas to potassium ion to a bunch of fluorine atoms. And then on the way back down we're going to be saving a total of, if we add those two together, 9, 4, 11, 1149 kilojoules saved. So we're actually going to have out more than we put in, creating an exothermic reaction, or an energy out reaction. And so when I subtract these two, I'm going to get a negative 562 kilojoules out. And so for this reaction where potassium solid plus 1/2 a mole of fluorine gas forms 1 mole of potassium fluoride solid, that has a delta H of formation, or a net energy change, of negative 562 kilojoules. Now, for any other problem where one of these other steps is missing, we know that the sum of all of these is that delta H of formation. So if they give us the delta H of formation, but we're missing one of these 5 parts, then we're going to be able to solve for that. Because from there, we can just count on algebra. Because any of these Born-Haber cycles are really just getting the metal into the gas form, getting the metal into cation form, breaking apart any bonds so that the atoms can react. If there's no breaking of bonds needed, there's no step there. Then we get energy out by making the anion, and we get a lot of energy out usually by making the ionic solid crystal from the lattice energy. And so all the ups minus all the downs gives us negative 562. That number may be positive, that number may be negative, but it's always the sum of all the ups plus the sum of all the downs. I hope this helped. Good luck.